about for graphing exponentials. Oops. We're going to graph this function. Notice that the base is 3.1, so that means it's growth, so we kind of expect a curve like this. So remember, when it was just a base to an exponent, we had the point 0, 1, and we had an asymptote at y equals 0. So it says to label the points and the asymptotes. So there's our asymptote, and there's 1 point. And the other points we're going to label depend on when we plug in and get to our power. So 3.1 to the first power is going to be 3.1. And then 3.1 to the second power would be something above 9. Okay, so we could go ahead and graph like this. If it involves a decimal or something like that, it would allow you to use a calculator to calculate the points. Otherwise, you should be able to calculate exponent values of them. All right, now we're going to graph negative 1/5 times 4 to the power of x. So first of all, understand that the parent function is just the y equals 4 to the power of x. And we have those basic features that we expect from an exponential growth graph. So we have the point at 0, 1. We have the asymptote. Oh, wow, that didn't work. Sorry. Okay. And then if we plug in 1, we would get like 4. Just want a couple points for reference. And the other thing I'm going to plug in is negative 1, because I know I always get the reciprocal, which would be 1/4. So that is the parent function where I have points at 0, 1, 1/4, and negative 1, 1/4. Now I'm going to take the parent function and I'm going to transform it this way. And from this, there's going to be a vertical reflection and a vertical compression by 1/5. So to list all the transformations, we would say a vertical reflection and a vertical compression, specifically by a factor of 1/5. Okay. All right, so now we're going to finish graphing the function, what it would look like in its final form, and list the domain and range. So first, recognize that the reflection is just going to put everything that was above the x-axis below the x-axis. So I'm going to just change all those points to below the x-axis. And think about how that changes the coordinates of the points. And I'm going to keep track here so that I can have them accurately on my graph once I'm done. The way the coordinates of the points would change is that we would now be at 1, negative 4, and 0, negative 1, and negative 1, negative 1/4. Now what we're going to do is vertically compress the graph by a factor of 1/5. So remember that vertical compression means that vertically we're trying to move some things back together. This gets a little more complicated in exponential graphs than it has been in the past, in the fact that there's two things to look at. There's an asymptote, and there's also a vertex point. In this graph, if you can use the asymptote as your thing to stretch or compress from, then we're going to use that, and if not, we would use the vertex. And what I mean by that is here, this is a vertical compression, so think, can you measure vertical distance from the asymptote? And in this case, we can, so that's what we're going to change the distance from. So that means the vertex point is also going to change. All three of these points are going to change their vertical distance from the asymptote by a factor of 1/5. Now, if this graph had a horizontal stretch or compression, it would be impossible to measure a horizontal distance from the asymptote because it travels horizontally. So we would then use the vertex point in that case. Okay, so what we're going to do is change all of these distances. So the vertex point is currently 1 unit away from the asymptote, and we're going to multiply that by 1/5. So we should change the point so that it is 1/5 of a unit away from the asymptote. So the asymptote is still at y equals 0. Finished? How was it?
Yeah.
Okay. All right, so our asymptote is still at y equals 0, and this point that was 1 unit away is now going to be 1/5 of a unit away. And I'm going to write what that point is now. So instead of it being at 0, negative 1, it's actually now at 0, negative 1/5. This other point down here was 4 units away from the asymptote. If I take 4 and multiply it times 1/5, I get 4/5. So I'm going to move that point so that it's 4/5 away from the asymptote, which means instead of being at 1, negative 4, that point is now going to be at 1, negative 4/5. And then finally, this point right here, it was originally 1/4 of a unit away from the asymptote. So it's going to get really close because when we multiply that by 1/5, we get 1/20th. Okay, so it should only be 1/20th of a unit away from the asymptote. That's really difficult for me to draw. So I'll just draw it really close, but I'll make sure I label it accurately. So it's at -1, -1/20th. And so this is our new exponential curve. And then I have the 3 points labeled there so you can see. And the last thing we should do is list the domain and the range. Now notice you can go left and right forever. There's no limitation on plugging in an x value. And we talked in class about there not being a vertical asymptote because we can plug in any x value we want. So the domain is all real numbers. And the range, notice that the graph travels downward forever, but it approaches the asymptote and doesn't cross it. So all the y values in this case are below 0. Okay, so we're going to do the same thing with the next one. Here's our equation. And notice this time we have a lot of stuff being added or subtracted, which means we expect translations. So the fact that there's a -2 in the exponent, that's a horizontal translation or shift. And we're going to shift to the right 2. And then the +1 that's after the entire exponential function is going to be a vertical shift. And that's going to take place by going up 1. Sorry, I said right 2, but I wrote right 1. So we're going to go right 2 and up 1 from our original parent function. And again, you have to be able to create your parent function. And in this case, the base is 3. So in our parent function, we're going to have our asymptote at y equals 0 and that point at 0, 1. When we plug in 1, we would get 3. When we plug in -1, we would get 1/3. So there's a couple of reference points along with that vertex point, and we can create our exponential graph. Now all we're going to do is shift all of these points to the right 2 and up 1. So I'm going to do that on my final graph right here since it's just shifting and it's not getting too complicated with reflecting and stuff like that. So this vertex point that was at 0, 1, to go to the right 2, the x coordinate is going to change to 2, and to go up 1, the y coordinate is also going to change to 2. So I'm going to move that right 2 and up 1. Okay, so the vertex point is going to be at 2, 2. This other point, that's height was originally at 3. Its x coordinate was 1, so to move to the right 2, it'll be at 3, and to move up 1, it will now be at 4. So that point is going to be at the point 3, 4. Oops, I forgot to move my asymptote. And then this point over here, that was originally at -1, 1/3. If we move that to the right 2, and then up 1, we're going to be at +1, 1 and 1/3. And one thing I did forget to do, you guys, is I forgot to shift my asymptote. And that will shift along with every other shift on the graph, the up and down shifts. It's the only thing that's going to affect our asymptote. So let me redraw that accurately. And you can see that the points follow the same pattern. We still have these 3 points, the same distance from each other and from the asymptote, but the whole thing has just been shifted. All right, and then for domain and range. So again, our domain is all real numbers for the same reasons as the previous problem. And this time our range is that everything is above 1, so we'll use that y is greater than 1. All right. So again, another exponential graph. This time notice that the base is 1/2, so we expect something shaped more like decay. But we have a lot of transformations happening in the exponent. Remember, those are going to be all of our horizontal transformations. When I factor out the 2, I can now see that what that's going to be is a horizontal compression by a factor of 2, because remember with the horizontal stuff, you multiply by the reciprocal, and that we're going to shift to the left 3. And our parent function in this case is an exponential function with a base of 1/2. And so remember, that looks like decay. And we know that we have the point at 0, 1. We have the asymptote at 0. And we can plug in a couple other points. So again, I'm going to stick with plugging in 1 and -1. So I get 1, 1/2, and -1, 2 to get this parent function graph. So now for the parent function, when I'm doing the horizontal compression of 1/2, notice I can't measure how far, like if I pick this point, I cannot measure how far it is horizontally from the asymptote, because to measure to the asymptote would be a vertical measurement. This is why horizontal compressions and stretches in the exponential function are based on the vertex and not the asymptote. So that means our vertex is going to stay in the same place. Currently, this point is 1 unit away from our vertex, but we're compressing by 1/2, which gives us a new distance of 1/2. This means any point that was 1 unit away from our vertex, we now want to be 1/2 a unit away from our vertex horizontally. Okay. So this is going to give us this new graph here, and I'm going to tell you what those new points are. So our point at 0, 1 hasn't changed. The point that was at 1, 1/2 is now at 1/2, 1/2. And the point that was at -1, 2 is now at -1/2, 2. Because they both scooted 1/2 a unit closer to that vertex. Now what we're going to do is going to take the whole graph and move it left 3. So in this case, because our shift is left, our asymptote won't change because it would only change with that vertical shift up or down. Okay. This point that is at 0, 1, if I move it to the left 3, is going to be at -3, 1. Okay. And notice there's a point that's 1/2 a unit to the right of that at 1/2 and 1/2 a unit to the left of it at 2. So there's the points placed all in the same place. Okay. Now remember, what I did was move them all left 3. So you could either figure out where they are now on the graph, or you could literally take all of their x-coordinates and just subtract 3 to see what they would be if you moved them left 3. So that would give us points at -3.5, 1/2, -3, 1, and -2.5. Oops, sorry, this y-coordinate here should have been 2. Yeah, I didn't change the y-coordinates. They all stayed the same. I just took the x-coordinate and subtracted 3 to show a movement left 3 on the graph. So again, the domain would be all real numbers. And the range is going to be that y is greater than 0. Okay, the next thing we're going to talk about is more algebraic. So you're going to be given a lot of different problems where things follow a growth or decay situation. And basically the equation they follow is that if you want to calculate the new amount or value, you take the original value or amount that it was worth. They use P often for principal. Now you want 100% of that, so you want 1/2 of it, plus you want an extra little part, which is the rate at which it increases. Okay? And that's all raised to an exponent of t, because every year it would increase again by that rate, kind of like your geometric sequence and series. Now, this would be for growth, because notice you're increasing it by a rate every year. If we were going to practice this in a situation where the value of something decays, we would still use the same equation, but we would be subtracting the rate yearly to show that it's decreasing in value. So using those equations, notice it says, okay, you buy a savings bond for $25. It pays a yearly interest rate of 4.2%. So that's important because that's the rate. And as a decimal, that would look like this. And then it says, what will the savings bond be worth in 15 years? So 15 years is the amount of time. And time is always in years in the equation that was given to you. Okay? And then our original amount we bought the savings bond for was for $25. So in our equation, to calculate what it's worth in 15 years, we would take that original $25 times 1 plus, because it's increasing in value, 0.042 for the 4.2%, to the power of t, which in this case is 15 years. So what we're going to do is put that into the calculator. You're welcome to add what's in the parentheses first, but just make sure that you get this entire value in the parentheses. So if you do this correctly, 25 times 1.042 to the power of 15, you should get that the new amount would be $46.34. It doesn't sound like a lot, but it just sat there for 15 years and it has a low percentage rate. All right, next one says you open a savings account that has a 4.5% annual interest rate. So we'll identify our rate. If your initial investment is $300, so that's our initial amount, or our P, or principal in our equation, You don't make any additional deposits or withdrawals, so you're just letting it sit there. How many years will it take for the account to grow to at least $500? So this time, T is the question, and we want to know when it's going to reach 500, so that's our ending amount. So we have that we want $500 to be the ending amount. If we're starting with $300 with a 0.045 interest rate, we want to know how many years that's going to take. So what we would do is we would take 500 and divide it by 300. That would be my first step here. And we get a value of like 1.6 repeating. And this is 1.045 to the t power. Now, right now, we don't really have a way to solve for what's in the exponent. So you could guess and check to try different values of t. Or what you could do is you could enter the 1.045 to the x power in your y equals, okay, and graph that. And you could look at the table, and you could see when it reaches as close as possible to 1.66666. So we'll see if we can figure that out. Let's see. It's going to be more than 1 because we have to at least have the amount we originally had. So when I look at my table, it looks like to reach a 1.6, it's somewhere between 11 and 12. 11, it's not quite there, and 12, it's a little bit past it. So I would say that you're going to need 12 years to reach that amount. And again, I just used my calculator to help me on this one. We'll have more of a way to deal with this at a little bit later date. All right, the next problem says the initial value of a car is $30,000. So that's our principal amount. After 1 year, the value of the car is $20,000. So that is the ending amount. And that's when the time is 1 year. And then it says estimate the value of the car after 5 years. So if we wanted to find the value of the car after 5 years, what we'd want to do is we'd want to take our $30,000 and do 1 minus, because it's decreasing the rate, to the power of 5. The problem is we don't know the rate. So what we're going to do is the other information from the problem, the fact that it was worth $20,000 after 1 year, we're going to plug all that into the equation to find the rate. So I'm going to divide both of these by 30,000. So I get 2/3 equals 1 minus the rate. Okay? And then if you finish solving this, what you'll find is that you get that your rate is equal to 1/3. Okay? So I'm going to go ahead then and plug that in here. So I have 30,000 times 1 minus 1/3. Gives me 2/3. Again, I'm going to raise that to the power of 5 times my original $30,000 amount to find my new amount. So in my calculator, I'm going to make sure that when I do the calculations, I have parentheses around the 2/3 when I raise it to the power of 5, and then multiply that by my 30,000. And I have $3,950.62, and that's very sad. That's a very low amount. All right, so basically what you should be able to do after this is you should graph exponential functions, which you saw the basic gist of them in class, and then what you saw here was ways to transform those graphs, and then you should be able to appreciate or depreciate or increase, decrease, growth or decay the values of original amounts as long as you know the rate at which they're increasing or decreasing and the number of years or some of the information surrounding that.